You ever wonder how a massive software project, like the Linux kernel with its 30+ million lines of code, manages to stay modern and secure? Well, it's not just about adding cool new features. A huge part of it is doing something that sounds, well, kind of backwards, deliberately getting rid of old code. Today, we're going to pull back the curtain on code deprecation, the real art of the cleanup, and see why it's one of the kernel's most important survival skills.
So here's how we'll break it down. We're going to start with the story of a failed experiment, which really shows why this cleanup is so vital. Then we'll dig into the philosophy behind it, check out the actual playbook developers use, and then take a little tour through a museum of old code to see this evolution in action. And we'll wrap it all up by talking about why this kind of digital janitor work never, ever stops. All right, to really understand why you have to throw code away, there's nothing better than a good old-fashioned disaster story. So let's dive into the cautionary tale of something called the SMC TCP upper layer protocol. So, on paper, this idea was brilliant. SMC is this super fast networking protocol, mostly used for big iron, mainframes. And this feature was supposed to be like an automatic turbo boost for your network. It would spot a regular old TCP socket and poof, magically swap it out for a high-speed SMC one, all behind the scenes. Your apps wouldn't have to change a thing. It's a free performance upgrade. I mean, what could possibly go wrong?
Well, as it turns out, a lot. And that quote you see, that's not from some random critic. That's from the kernel developers themselves. They looked at their own work and had to admit it wasn't just a little buggy. It was, in their own words, fundamentally broken.
So here's the anatomy of that failure. The flaw was this. To do that speedy socket swap, the code was changing core kernel structures after they were already up and running. Think about it like trying to swap out the foundation of a house while the family's still inside making dinner. It just doesn't work. It violated the most basic rules of the virtual file system, the VFS, which is like the absolute bedrock of how Linux handles files and sockets. And the consequence? A ticking time bomb of security holes and nasty crashes called race conditions. The only safe thing to do was to get rid of it, the whole thing.
And this slide shows the right way to do it. Instead of performing risky surgery inside the kernel, you do the work from the outside. The safer, modern approach is to use tools that live in user space, like BPF, which lets you run these tiny, safe programs inside the kernel, or LD_preload, which can grab function calls before they even get to the kernel. These methods achieve the same goal without cracking open the engine and messing with its core machinery.
Okay, so this brings us to a really important question. The problem was obvious, sure, but why completely tear it out? Why not just patch it up? The answer really gets to the core of how the kernel development world thinks.
Because that decision to remove it instead of trying to fix it wasn't just a one-time thing. It points to a much deeper philosophy that's absolutely central to the kernel, a culture of non-stop evolution and cleanup.
And this quote right here says it all. Now, the public-facing stuff your apps talk to, famously stable, but inside the kernel, it's a completely different story. The internal plumbing is always changing. And here's the key. That's a deliberate decision. It's not a bug, it's a feature. It's what allows the kernel to get faster, more secure, and to innovate without being chained to mistakes made years ago. So deprecation isn't really about destruction. It's about creation. It's how developers make way for real progress. It's how they fix those deep design flaws that you just can't paper over. It's how they adapt to shiny new hardware, get rid of old, dusty code that nobody's using anymore, and ultimately, how they keep the kernel from bloating into an unmaintainable mess.
So if change is the only constant, how in the world do you manage that across thousands of developers without it all turning into chaos? Well, you need a playbook. So let's look at the actual tools and the conventions that developers use to manage all this cleanup. First, let's just get on the same page about what deprecation actually means here. It's not just someone hitting the delete key. No, it's a whole process. You officially mark the code for removal in the future, you give everyone a heads up, you write down why it's going away and what the new, better way is, and you set a timeline. It's like a managed, careful demolition.
One of the most direct tools in this playbook is something built right into the C language itself, the __ deprecated attribute. Developers can literally stamp this thing onto a function right there in the source code. It's an unmissable signpost that basically yells, hey, this is old and it's going away soon.
But here's a super interesting twist, and it tells you a lot about how pragmatic kernel developers are. You'd think that the _deprecated tag would set off a bunch of loud warnings when you compile the code, right? Well, it used to, but the kernel has this very strict build with zero warnings policy. There were so many deprecation warnings that developers just started tuning them out. It was classic alarm fatigue. So what did they do? They turned the warnings off. Now the tag is just a silent note, a marker for automated tools and for developers who are paying close attention.
And this whole process isn't one size fits all either. Different parts of the kernel have their own specialized tools. For example, that powerful BPF subsystem we talked about, it's got its own special flag, KF deprecated, just for marking its own specific functions for removal. It's a great example of how this cleanup process is tailored for different parts of this giant code base.
So the key takeaway here is that it's a whole toolkit working together. Yeah, documentation is crucial, but it's backed up by automation. The kernel has this script called checkpatch that acts like a vigilant bouncer for every single piece of code that tries to get in. It's programmed to automatically flag when someone tries to use old, unsafe functions. It'll call you out for using a function that can cause overflows or an outdated memory API or a dangerous error handling pattern. It's an automated code janitor, and it's relentless.
All right, now for the fun part. Let's take a little walk through the museum of superseded code. Seeing these concrete examples really brings to life how much the kernel has evolved over all these years.
Take a look at these old functions for finding PCI devices. They all got replaced by new ones that start with PCI get _. Now, this isn't just a simple rename. The new versions are way safer because they correctly handle something called reference counting. That's just a fancy way of keeping track of who's using a device at any given moment, which is absolutely critical on modern computers where you're plugging and unplugging stuff all the time, like a USB-C dock. The old functions could get really confused and crash the system if a device just vanished.
And you see the exact same story with timekeeping. The kernel used to have a bunch of different ways to get the time, which, as you can imagine, led to some really subtle and hard-to-find bugs. So all of those were eventually consolidated into one single unified KTime API. This kind of cleanup makes sure that every single part of the kernel is speaking the same language when it comes to time, which is just critical for everything from scheduling to logging. It's a perfect example of making things simpler by modernizing them.
And this is probably the coolest part. This goes way beyond just function names. Entire ways of writing code, entire conventions get deprecated. For example, it used to be common to use bug on to check for an error. But that function panics and crashes the entire machine. It's like using a grenade to kill a fly. The modern way is to use warn on, which just logs a helpful message. Same thing with controlling GPO pins. The old way was messy, but it's been replaced with a much safer, modern interface. This shows how the whole culture evolves towards being more robust and more secure. Okay, that brings us to our final point. And the big insight here is that this whole cleanup process, it's not a project that has a start and an end date. It's a fundamental, living part of how the kernel is developed.
You see, a code base that's been growing for over 30 years isn't really like a building. It's more like a giant ancient garden. You can't just tidy it up once and walk away. This constant, disciplined process of pruning away old branches and weeding out bad patterns is exactly what allows the kernel to keep growing and adapting without collapsing under its own weight. It's a really powerful statement about choosing long-term health over short-term convenience.
And all of this really leads to one final thought. The Linux kernel's disciplined, almost religious approach to cleanup is a massive lesson for any software project, big or small. And it makes you wonder, right? What outdated functions, what insecure patterns, or what fundamentally broken ideas are hiding in the code that you work on every day?